morning. Today I would like to introduce Dr. Gabriel Taubin. Dr. Taubin is a scientist from the IBM Thomas J. Watson Research Center. And Dr. Taubin was elected IEEE Fellow for his work and his contributions to the field of geometric modeling. And also, Dr. Taubin was one of the main architects of the MPEG 4 standard. He designed the geometric compression for MPEG using topological surgery. So Dr. Taubin is going to talk about signal processing meshes, and I'm pleased to introduce Gabriel.
Sorry. Well, thanks for the introduction. It's a real pleasure to be here to celebrate the 50th anniversary of IMPA, and a great opportunity to come to Brazil. What I'm going to talk about today is more or less an overview of a few projects that we've been working on for the last few years, and a little bit of give you a flavor of what is involved in some of the mathematical problems. One thing you will notice is that the mathematics here is rather simple from what I have been hearing during the whole conference. But that's not an accident, it's on purpose. In graphics and visualization, we have the freedom to choose the mathematical tools that we need to model our problems. And the simpler the tools, the better. And in particular, because we deal normally with very large data sets, and the simpler and less complex algorithms is much better. So let's get started. This is more or less work that I have been doing when I was leading this group, say from mid-95 to around 2000. The goal there was to develop techniques to make the use of 3D content useful in the web. I mean, we were at the peak of the internet hype, so it was very important to develop techniques to be able to show 3D content there. And we work on all the aspects from capturing the data to compression, transmission, and visualization. And I'm going to go briefly to some of those. Some of these things I'm going to touch sort of briefly and in a superficial manner, and some other things I will try to go a little bit in more detail. And in particular, the last topic, I mean, it's a little bit more mathematical, where I have been trying for a few years to get ideas from the signal processing field and try to port those algorithms to the regular case of meshes. So we will see what happens there. And of course, some of these projects, particularly those that had programming intensive deliverables within the company, well, a number of people participated in these projects, sometimes partially, sometimes full-time. So some of the credit for some of the results belong to them. At the end, I mean, I'm going to show you a couple of pictures of one little project that I did last year while I was at sabbatical Caltech with a couple of students, where we took a digital camera, commercial product, and we reprogrammed it to make it work as a 3D camera. Okay, so most of the talk will be about polygon meshes. Polygon meshes have become in graphics essentially the standard representation, mainly because the graphics hardware, I mean, it's a very simple primitive, it's very, very simple to process and display a lot of polygons per second. And most of the techniques to recover shape, 3D scanning based on laser triangulation and other techniques, generate one way or the other polygon meshes as an approximation of smooth surfaces. Isosurfaces are very popular in scientific visualization, medical imaging, essentially level sets of continuous functions defined in a grid. And then lately, another area that has become very popular in modeling animation is subdivision surfaces, where you take a polygon mesh and you partition the faces into smaller faces and you smooth the result, and you keep going that way. So what is in common in all of this is that in the end, you end up with very large meshes, millions, even in some cases billions of polygons, and you want to operate on this. So one first problem you have to deal with when you capture data, if the data is noisy, how to remove the noise. I mean, how to make the surfaces smoother, for example. How to change the sampling rate. If you have too many polygons, how do you reduce the number of polygons but preserve more or less the geometry of your shape, or the opposite? How do you increase sampling in some areas and still preserve the number of the shape of the objects? But then in animation, you may want to interact as if it were clay. I mean, you want to modify the shape in one way or another, and of course, because of the fact that we have so many variables, the position of the vertices, we cannot just pick one vertex at a time and move it from one place to the other. We have to find a way to do some more global operations in a more intuitive way. And of course, there is the internet, and the issue of saving this data with a minimum number of bits, so that there are the issues of how do you represent this data in a more compact way for efficient storage, and of course for transmission across the internet or whatever. So well, of course, the last point is the important one. These are very large data sets again, so you have to worry about the complexity and the speed of your algorithms. So in general, any algorithm that is more complex than linear is not acceptable for almost anything. All right, so one main thing about polygon meshes, you can think of, make a parallel with images and video. The difference here is that we have sample points, the vertices, and they are interconnected in an irregular fashion. And that's the main difference, that we have to deal explicitly with the connectivity. So that's the combinatorial part. And the geometry, the location of the vertices, and maybe colors and other properties that are there to be able to shade or the meshes can be dealt more or less with ideas from the regular setting. And of course, once we talk about the connectivity, we have to worry about the topology and so on. And in most of the cases, we are going to work on methods that work on manifolds, and there are extensions to the singular cases, but I will not have time to talk much about that. So let me spend a couple of minutes on scanning. So this gives you an idea of the complexity of the scene. This is a project we ran something from 98 to 2000, about 2 years, where we worked with an art historian who has been studying this statue by Michelangelo for many years. This is a statue that Michelangelo built when he was sort of old. It's in Florence, in the Museo dell'Opera del Duomo. And at some point, he started to break it in pieces and left it on its side. And one of his students eventually put it back together, and that's what we see today in the museum. The statue is not fully finished. There are some parts that are polished, and there are some parts where you see the tool marks. And this art historian had some hypotheses about what had happened with the statue, so he wanted to do a more scientific study, in particular looking at the statue from viewpoints that are impossible today because the statue is on a table in a different place. He wanted to remove the parts that Michelangelo removed. He wanted to measure, take the figures and stretch them up and measure the dimensions of the body parts and so on to see whether the proportions were right and wrong and so on. But for us, it was a challenge in trying to understand what were the limitations of the technology for scanning at the time. Laser scanners are very accurate, but they were outside our budget, so we couldn't use laser scanners for this project. And so we used another technique called based on structural lighting, where you project a pattern and then you try to recover the shape from that. And so the picture you see there on the right is a reconstruction. It's a rendering of the model that we reconstructed from a viewpoint that today is impossible to get because the ceiling is on top of the statue there. So as a comparison, on the left, you see a picture of the real picture of the statue as it is now, and on the right, a rendering of just the geometry that we recover. In the little corner on the right, we see a more detailed piece where, I mean, we didn't only recover shape, we also recover colors and so on. And the rendering on the right is the detail of the statue with the colors included. But the complexity of this is a schematic of the method. Our shape camera essentially was taking pictures the size of the face of Christ there. And we covered the statue. I mean, we have to go around, take a lot of these 3D pictures, and in the end, we had something like 1,000 of them. Some of them overlap, and some of them don't. And put all of this data together as a single model. And in addition, there is the issue of the fact that our scanner didn't have enough resolution to resolve the details, such as tool marks and so on. So we needed more resolution, and the way we did this was to have a hybrid representation where the geometry is represented at the resolution we could get, and the details, like tool marks, are represented with textures. So these textures contain normals, actually. It's what is called in graphics normal maps. And these normals can be used for shading, and you will see in a second what it is. But the technique that is used to recover these normals and the color and separate information is called Photometric Stereo. Essentially, the idea is the following. If you take a picture from a light source here, and another picture from a light source here, another picture from the light source there, and assuming some simple surface properties, you can estimate the normal vectors and separate the color from the multiple pictures. And that's what essentially we use here. And the other thing was, once the data is recovered, I mean, this model in the end was something like 15 million polygons, and this was 2 years ago when the computers were 5 times slower than now. So it was still difficult to interact with this model anyway, at the full resolution. So we had to develop a way to visualize the data interactively faster rates. So our solution is something like this. On this viewer that we developed on the left side has a simplified model of the statue. So it has a lot fewer polygons. And so you can move around and choose the viewpoint at interactive speeds. Once you choose the viewpoint, so you see there is a little square in the middle, you access the full database on disk, and you reconstruct a full resolution version of this particular part, and it's displayed on the right. And then on the right, rather than moving in 3D, when you move the mouse, the light source moves from one place to the other. And so you can see details that are in the texture that you cannot see otherwise. I'll give you an example. So the picture on the left, for example, here is what happened when you move the camera around. So there are some details that you can see if you could move the full resolution picture around. But in our case, we just move the light source around in the full resolution picture, and essentially you can see the same details, and it's more efficient in terms of interaction and storage and so on. Well, before that, of course, we focused in this project on the algorithms necessary to put all of this together, and there are a lot of details there that I will not have time to explain. So this will give you more or less a flavor of one aspect of our work. The other area where we spend quite a bit of time is this area of geometry compression, essentially how to encode these meshes with a minimum number of bits for efficient storage and transmission. And in this area, our main contributions were this so-called, what we call it, topological surgery, and you will see why in a second, method to encode the connectivity of the mesh. Remember that here the connectivity is completely arbitrary, and we have to deal with the connectivity explicitly. When you compress images or video, you don't have to do anything about that, because you know it's a regular grid of so many rows and so many columns. You just say how many rows and columns, and that's it. But in here, we have to say not only how many vertices we have, but we have to explain how they are interconnected. And in such a way that the decoder on the other side of the wire could reconstruct that connectivity and then place the right vertex positions in the right place. So we developed a method. The first method is static. I mean, you may be familiar with JPEG, where sometimes you can download the images progressively, it comes low resolution and then details. Well, we also developed a method to do that progressively. And then we spent 2 years pushing this technology into the standard, MPEG 4. And now it's part of the standard. And in that process, we had to help write the specifications, develop the reference software that is part of the standard. And then within IBM, we transferred that technology to a product that is called Hot Media. The main thing about this is that, well, this topological surgery scheme was the first method proposed in general to encode the connectivity of a mesh with no loss of information. Since then, a number of other people entered the field, and there are methods that are more efficient than this, but they are sort of research kind of codes. This has been developed essentially as at the level of a commercial product. Anyway, Hot Media is a product that we helped develop with this technology, and it allows you to put 3D content on your, well, and some other types of data types on your website. It has two parts. What you see on the left, there is a Windows application that allows you to import your model into the tool and then choose some very simple compression parameters and say the data compressed. And then the viewers that we also develop are written in Java, which means that you don't have to install you don't need a special hardware, and you don't have to install any plugin or anything to display these models. And by the way, this is free, so it's something that you can go download and use to show your results. The 6 pictures on the right are some screenshots of the applet. And I'm not going to show a demo of that, but I'm going to show you another tool that is based on this, and you will see what you can do with that. But I encourage you to go and play with that. Anyway, so let me start giving some details about what's going on here. Topological surgery. Why do we call this topological surgery? Well, the idea is that the data is transmitted sequentially, but the structure of a surface has no sequential order to start with. So we have to do something to represent this connectivity in a sequential way. So the idea is that, well, there is this something used in graphics, has been used for a long time, the so-called triangle strips. That is something that is used to send triangles from the CPU to the graphics adapter. If you have to send the triangles one by one, independently of each other, you have to send the 3 coordinates of the vertices multiple times. But if the next triangle you send is next to the previous one, it has 2 vertices in common, you just send 1 vertex. You say, well, keep the last 2, remember the last 2, and the next triangle is composed. I mean, I send you 1 vertex and you connect it with the previous 2. So if you the idea of triangle strips is you put a lot of triangles one next to the other, and you just send 1 vertex per triangle. Now, when you take a mesh and you cut it in triangle strips, which is by itself a difficult problem because you ideally would like to have a single strip that covers the whole thing, and that may be impossible, and generally it is impossible, you lose some of the connectivity information because as you cut, you still are going to be sending the vertices on each side of the cut twice at least. So in our case, we wanted to preserve that information of how things are cut. I mean, first of all, there is a problem that you cannot have a single strip. So what you can do is cut and decompose the triangles into a tree, and then preserve the information of how things are cut. So let's see how things work. Suppose that you take a simple mesh, something like the shape of, well, not the shape, the topology of a sphere, and you choose edges on the graph of the mesh which form a spanning tree, which means that it's a tree that touches all the vertices of the mesh. what happens topologically when you cut through a tree? When you cut through a tree, so think about a flat sheet of paper. You draw a tree, you cut through a tree, you're making a hole, essentially. So you're converting the sphere into a disk. Now, because of the fact that our tree touches all the vertices, you end up with a triangle mesh that has the topology of a disk. So it has a single boundary, it's a long loop, but it has all the vertices in the boundary. And so it turns out that when you look at the Euler formula for a sphere, those triangles have to be connected, forming another tree, essentially. The dual of a simple polygon that is a loop which is triangulated is a tree. Okay. And then, well, the main thing is that when you look at these triangles now, well, the tree that interconnects them is not sufficient information to establish, to describe the triangulation of this polygon. So there are a few additional bits that need to be transmitted. And so, well, this is difficult to see, but because of the main thing is that suppose that we want to describe the triangulation of this polygon, and we're going to enter the polygon through this edge here, and then start moving. Well, every time you enter a triangle, there are two opposite edges, one on the left and one on the right. Each one of those may have a triangle after or not. So you can use 2 bits per triangle to describe how this thing is connected. So for example, so it's difficult to see, but this picture shows you the order of traversal. So you visit this, and that. And here, because of the fact that we have 2 branches coming out, we go first to the left, and when we finish with the left branch, we come back and go to the right. So we recursively traversal the whole thing. So the encoding of this triangle, for example, we use 1 bit, the first bit to say that there is something on the left, and the second to the right. So numbers between 0 and 4, 0 and 3, one of those numbers for each triangle. So for example, this one says 1 because there is something on the left. The second triangle says 2 because there is something on the right, and so on. When you reach a branching triangle like this, it says 3 because there is something on the left, up something on the right. And the triangles that are at the end, the leaves of the tree, have a 0 because there is nothing else. So, well, it's almost impossible to read, but this string of symbols that we have here in the bottom, oops, running out of battery, well, encodes the triangulation of the polygon. So you say how many vertices it has, and then you send this string of 2 bits per triangle, and that establishes the correspondence, the triangulation. And this, in addition, because we take care of trying to construct this triangulation so that there are very few branching points and leaves, can be run length encoded. That is, long strings of 1s and 2s can be compact, and there are some engineering tricks, entropy encoding, that we can do on top of this. So the bottom line in all of this is the representation of a simple polygon is composed of the following. A vertex tree, that is the spanning tree that was connecting the vertices in the original mesh. That is the information that we will need to restitch the mesh back together in the decoder. The structure of the simple polygon, this 2 bits per triangle string that tell you how to triangulate the polygon. And then in addition, of course, for example, in the vertex tree, we have 1 node per vertex. We can, in the order in which this tree is traversed, we can add the vertex coordinates there, which are quantized and entropy encoded as well. And the interesting thing about all of this is that in order to stitch the mesh back together, which means you have to establish correspondences between pairs of boundary edges in the polygon, you don't have to send any additional information. The traverse, I mean, suppose that you draw a tree on a piece of paper, and then you go around with your pencil making a loop. Well, this correspondence, I mean, the correspondence between these 2 pictures is implicit and is what allows you to restitch the polygon back together. Well, one thing that I have to mention is, of course, if the topology of your mesh is more complex, if it has handles and so on, there are more things that you have to add. But in that case, what you do is you first interconnect the triangles forming a simple polygon. So you construct a spanning tree in the dual graph, and then you look at the remaining edges. The remaining edges are no longer a tree. They have loops because of the handles, but the number of loops is exactly twice the number twice the genus of the surface, so there are very few of them. And there is an additional information that has to be encoded. Okay. And the way we construct this trees is the most efficient way. Well, the coding here is the following. Red means a leaf polygon. Yellow means a polygon that is in the middle of one of these strips. And blue means a branching polygon. Well, when you have something that is composed of quadrilaterals or other polygons like this, you do the same construction in the dual mesh, and then as you traverse the polygons, you triangulate on the fly. So you convert into a triangle mesh, and you have to add more information to decide which edges are true edges, which ones have to be removed. And what we want really to improve the entropy of the representation is to minimize the number of branches. And the most efficient way to do that is to start from a polygon and start spiraling around. The problem is that, of course, sometimes you get stuck, and so you have to backtrack and start another branch in a different point, and that's what gives rise to the branches. I'm going to keep this. I have a bunch of demos scattered around, but if I show all of them, maybe we'll run out of time. So that work was done more or less in '95 and was the basis of all of this MPEG-4 and the other work. This is more recent. It's some work that I did last year, and it's closely related. Suppose quadrilateral meshes with quadrilateral faces have become quite popular lately, particularly because of subdivision surfaces and so on, but in finite elements, they have better properties as well. So the question is that, we would like, of course, to do something special for quadrilateral meshes because they are important. So the idea here is that we have the freedom for each one of the quadrilaterals to triangulate it in one way or the other. So we have one of the two diagonals we have to choose, and then interconnect these triangles in one way or the other. So it turns out that for a quadrilateral mesh, you can always choose the diagonals in such a way that you interconnect all the remaining triangles forming a single loop, a Hamiltonian path, which is quite interesting because in the case of triangle meshes, the problem of deciding whether the Hamiltonian path exists or not is NP complete. But for quadrilateral meshes, because of the fact that you have this freedom, you can always interconnect divide the faces along one of the diagonals and interconnect the polygons, the resulting triangles forming a single Hamiltonian path. And the idea is very simple. So the idea is that you split the quadrilaterals along one of the edges, and then you link the remaining triangles along the edges, the original edges. So we never link them along the diagonals. So every triangle is connected to two neighboring triangles, which means that whatever choice you make of the diagonals, the resulting triangles are going to be interconnected, forming cycles in the dual graph. I mean, at least for a manifold. I will explain the last point later. And the question is, so you see here a picture. Here you have a quadrilateral mesh that is thick. I mean, it's a manifold. We choose the diagonals are random, and these colors show you the cycles that are formed. Now, the interesting thing here is that, if you take a quadrilateral that is separating two cycles of triangles, and you flip the diagonal, you reduce the number of cycles by 1. So it's a trivial algorithm to start searching for these quadrilaterals, and every time you find one that separates two different cycles, flip them. And after a while, in a finite number of steps, in a linear number of steps, in terms of the phases, you end up with a single cycle. And that's the main idea. The question is that it's not only that you can find one, you can find a lot of ways of doing this. And the interesting thing is to figure out which one is the best. So for example, here you have a little zooming on some of these meshes using different schemes to choose how to choose the diagonals. Now, what is the difference between these two? Well, the latest graphics adapters, I mean, you remember that I mentioned triangle strips. For triangle strips, you have to remember just 2 vertices to be able to render the next one, and then you drop the last vertex and you keep going. Newer graphics adapters have a much larger memory in the board, so they remember something like 16 vertices or so, or maybe more. In that case, if you can save a lot of time sending data from the CPU to the graphics adapter by organizing your triangle strips so that they come back to the same vertices very often. For example, in this case, the vertex on one side of the strips will be visited back after a long time, so after too many triangles. And so that means that it will not be in the cache, and you will have to send it back again. While if you have something like this, that the strips keep going back and forth, the vertices in the cache are reused more often. And it turns out that this is close to optimal in terms of usage of the cache in these new graphics adapters. Okay. So let's see, maybe I can do a little demo. So let's wait until this thing. So here we have a famous bunny. So, but this is not really the bunny. So this is a tool that I have been developing over the years to develop new algorithms. The rendering part is all written in Java, and the rendering part is very much what I mentioned before, that is part of the hot media product. So what I'm going to do now, for example, is, so you will see that how fast, this doesn't have a lot of vertices, but anyway, the algorithm is done. What we see here is the green edges here, the diagonals chosen. This, let me get closer there. Oops. So the algorithm has already run. It has chosen these blue quadrilaterals as those where it had to make flips. The original, so these are the loops, you see. Let me do something more to show you this. So what I did here was to cut through the diagonals and split the mesh a little bit just to illustrate what's going on. And you see that if you choose the diagonals at random, you create a lot of cycles, right? But with this very simple idea, reset, do it again. So you see that you end up with a, well, you don't see because it's too complex, but the thing is that all of these triangles are interconnected, forming a single cycle that goes over all the triangles. Anyway, let's keep going. Where's my pointer? All right, so maybe now we'll switch gears and talk a little bit about this signal processing approach. So now we are going to focus the connectivity. I mean, so far I talked about things that have mainly to do with connectivity, combinatorial problems. Now the connectivity is fixed, and we're going to deal with the geometry. And the idea is something like this. You want to develop a method. I mean, data is noisy when you capture it or when you generate it. Sometimes algorithms have artifacts. So you would like to develop methods that very fast will remove the noise and will preserve the shape. And my motivation has been to look at the signal processing literature and try to see which of those algorithms can be converted into things that algorithms that are useful in this setting. Okay, so that's what I just said. And the thing is that in signal processing there is a large body of literature, and it's well known how to solve all of these problems. The difference with our setting is that some of those algorithms just do not extend to the irregular case, or do not extend in any efficient way. So I'm going to talk about one particular thing that I did a few years ago that essentially give you a flavor of the kind of problems. So for example, here we have some noisy data. One simple way to denoise the data is to run the heat equation, on the mesh essentially, which in the image processing literature is called Gaussian smoothing, or in the mesh processing literature is called Laplacian smoothing, which means that you take every vertex of the mesh and you replace it by some weighted average of the neighbors. You do that for all the vertices, and then you replace all at once, and you keep doing this over and over again. The problem you have with that is that you see the kind of problem you have. There is a big distortion of the shape. And the problem was at the time, well, how do we fix this algorithm? What do we need to change to make it preserve the shape and still remove the noise? Okay? And the reason why I like this much is because the solution that you will see has to do with changing one sign in the algorithm only. And that's my goal in general, try to find very simple algorithms to solve this problem. So this is sort of representative. So again, the connectivity, we have vertices, they're interconnected with these polygons. We only look at the graph defined by the edges of the mesh. And a signal is one value for each vertex of the mesh. So what I'm trying to do here is to formulate this as a matrix with problem. In mesh generation, Laplacian smoothing has been used to improve the quality of the triangulations. In that setting, the boundary is fixed. You insert vertices in the middle and you interconnect them, and then you essentially do what I said. You define a new position of a vertex as the weighted average of the neighbors. And then you compute this as a function of the original data, and then you move to this position. You can also write it in the following way. You define the Laplacian vector, the weighted average of the vectors that go from the vertex to one of its neighbors. And once you compute all of this, you move the vertex moving in that direction by, say, 1/2 or something like that. In our setting, we don't have any constraints. We don't have fixed boundaries, so we do the same thing. This is Laplacian smoothing in general for mesh denoising. For every vertex, you compute the weighted average of the neighbors, and then you move in that direction by lambda. And of course, as we saw before, the noise is removed, but the shape is distorted a lot. So let me give you a little demo of that. So for example, here we have some noisy data. And I'm going to apply here 10 steps of this Laplacian smoothing with lambda equal 0.6 something. And you will see what happens. So it gets smoother. And now I'm going to apply 10 more. And 10 more. And if you keep applying this, you see the thing gets smoother and smoother, but the distortions are so big that you cannot really. One thing that people have tried to do with this is say, well, let's compute the volume of the shape and then expand it to preserve the volume, but you're not removing the distortion. So there is an intrinsic problem. The algorithm, as you see, is very fast, but it doesn't work. Okay. So the idea here is you will see that the solution is a change of sign, but the analysis is the interesting part. So let's start by looking at the classical case. We periodic signals defined on one-dimensional periodic signals, so signals defined on a polygon. The same thing. We know that there is a discrete Fourier transform. So every signal of this type can be expanded as a linear combination of the complex exponentials. And there exists a very fast algorithm to actually compute the decomposition. So one thing that people in image processing has done for a long time is say, well, if we can expand something in Fourier series, let's drop off the tail of the decomposition, and the low frequency modes are going to give you a smooth version of your shape. Well, of course, we can do that here because we have the fast Fourier transform to actually compute this efficiently, but we don't. Well, first of all, there is the issue of figuring out what this means in the regular setting. So we have our Laplacian smoothing step. We write this in matrix form, where, well, K is just the negative Laplacian the standard way. Well, the matrix K, the Laplacian matrix, has eigenvalues that, under mild assumptions, they are real, and between 0 and 2. I mean, and of course, there are the corresponding eigenvectors. And these eigenvalues and eigenvectors, as you well know, well, first of all, theoretically give you the same decomposition, although we cannot compute them. And also, they have the right meaning. I mean, when you look at the geometric meaning of the formula on top for a low frequency mode and a high frequency mode, the eigenvalue essentially is the average length of the displacement of the Laplacian vector. So for low frequencies, it's small, and for high frequencies, big. And here in the bottom, you see some of these eigenvectors plotted in color-coded and so on. So it's the same meaning. It's just that we have the problem of computing this thing. We don't have the fast Fourier transform. In principle, we would like to do the same. Compute the first few Fourier coefficients and drop the rest, and then reconstruct. But we cannot do this because these are very large. I mean, we're talking about computing eigenvectors of extremely large and sparse matrices. So this is not really possible. We need all of them, actually. So the solution here is the same that people do in signal processing. Rather than computing the exact filter, the low-pass filter that we have on top, we will compute an approximation. An approximation is a polynomial, for example. We can, you will see in the next foil that if we have a polynomial, well, f is a polynomial, or some function. If we can find a function that is close to 1 for low frequency and close to 0 for high frequency, and we are able to evaluate the expression at the bottom, then we are done, because that would be some sort of approximation of our filtering. Now, what happens with functions of matrices? So if we take a polynomial, a univariate polynomial, of course, a polynomial evaluated in a matrix gives you another matrix of the same size, which has the same eigenvectors, and the eigenvalues are the function evaluated in the eigenvalues. So the only thing you have to do is design this polynomial so that it's close to 1 for low frequency and close to 0 for high frequency, and then figure out how to evaluate the expression in the bottom. F of the polynomial times our signal is what we want to evaluate. And it turns out that evaluating a polynomial in a matrix times a vector, the only thing you need is to know how to multiply a matrix by a vector and by a constant. So that is doable. And well, this is the so-called, in signal processing, the finite impulse response filters, filtered with a polynomial transfer function, and this can be done here efficiently. So yeah, well, that's just what I said. Essentially, you don't need to compute any Fourier transform. You just evaluate the expression on the left. And what happened with Laplacian smoothing? Well, the polynomial in Laplacian smoothing after n steps is something like this. So when you look at the behavior of this, clearly for any frequency other than 0, this goes to 0. And that is what shows that explains the behavior of our algorithm. So if you keep applying this infinite number of times, the whole shape converges to a point, to the centroid. Well, so this is the solution that I propose. I mean, rather than, it's very simple. You do a first step, Laplacian smoothing, with a positive lambda, and then you do a subsequent step of Laplacian smoothing with negative scale. So you try to undo what you did in the previous step. So it's the same computation, it's just that you change the sign of the lambda. And well, when you do this, I mean, you look at the expression inside, it's a parabola upside down like this. And when you take powers of this, it gives you the typical low-pass filter design. So let's see how much. I mean, so as you see, it's the same computation, except that we keep alternating between two different values of lambda, one positive, one negative. So let's see what happens if we apply this filter. So with the same shape, I'm going to switch to this my method. So now there are two lambdas. This is positive, this is negative. But I'm going to apply the same number of steps as before, 10 steps. We'll see what happens. So we apply this, and the mesh gets smoother. So this is not very different from the other, but we're going to apply more. Apply 10 more, and 10 more, and 10 more, and so on. And if you keep applying this, let's put here, for example, 10. I'm going to do 10 steps of 10 steps each. So you see that the mesh keeps changing, of course, because this polynomial is not exactly 1 for low frequency. It's a little bit above, so the low frequencies keep increasing slowly, but very slowly. So that is what makes this thing useful. Okay. Next thing. So this was I did this in '95, and there have been a number of extensions and improvements because when the mesh is not very regular in terms of there are some polygons that are edges that are longer than the other, there are some artifacts that you need to fix, there are boundary conditions and so on. But it's a very simple algorithm that people use. One extension that I did as a result of a visit to Stanford a few years, soon after I did that, was to be able to show, define an efficient algorithm to implement an arbitrary polynomial rather than expanding the polynomial the usual way. This is more stable and works very well. And once you have this, you can use the standard techniques to design filters, to design the filters you want. You can do not only low-pass filters, you can do enhanced middle frequencies, whatever you want. And it's the same amount of computation. Well, there have been a number of other topics that I've been looking at, and other people have been looking at, but I will not go into any of those. I will just show you some pictures. For example, there is the issue of doing this smoothing with constraints for design purposes. So you may want some curves to stay sharp in the middle of your shape. In that case, you can play with the weights of the Laplacian smoothing. So for example, to do this, the curve in the boundary evolves as a curve. So the neighbors of points in the boundary are other points in the boundary, not points inside the surface patches, but the points inside the surface which are neighboring the boundary, they use the information in the boundary to move. So that the result is that the curves evolve as themselves and the rest of the surface follows. And so you can do things like this. Another thing that I did recently, last year actually, there are some problems. This Laplacian smoothing scheme for design is very nice, but you don't have controls of the normal. Sometimes you can say this edge has to be sharp, but you also want to specify what is at what angle the surface meets the edge. So the idea here is to do a second order scheme where we look at the normal vectors to the surface, and we want to first of all smooth the normal vectors to the surface and then integrate them so that move the vertices so that these normal vectors become the normals to the faces. So this illustrates how things work. For example, we start with this very regular shape. It's a set of cubes, and this is the surface, the boundary of that. So we take the normals to the faces that are just 6 possible directions. And, well, the main problem with extending Laplacian smoothing to signals that are which are constraints, such as normal vectors that are length 1 defined on the sphere, is that if you just apply the usual rule of averaging the neighbors, you end up with a vector that is no longer unit length. But there is a way to do this, and the way to do this is you redefine what is the meaning of the Laplacian vector. Essentially, displacement became rotations in the unit sphere, and there is a very simple formula based on the Rodriguez formula to do this computation as efficiently as in the Euclidean case. So we can smooth unit length vector fields, and this is what we get. So here is the same geometry, but I'm using the new normals to do the shading. And then there is an anisotropic step where instead of weights in the Laplacian smoothing formula, there are these W's that are weights, they are scalar they're numbers. We replace it with matrices, so it's essentially a tensor there, where you give more weight to the displacement along the normal direction and less weight to the displacement in the tangential direction. The result of this is that you start moving the vertices to integrate the normal field in the least square sense. Let's see. How much more time? I don't know. What time did I start?
About 10 minutes.
10 minutes. Okay, so let's wait until this thing loads. It's going to load a little, rather large mesh. So here we have a, let's see. So this has about 50,000. Where is my pointer? Here. Sort of low. So you see what we have here. This is an isosurface, so it's a level set of a medical CT, where we just put a level and decide which voxels are above the threshold, which ones are below, and this is the boundary of this set of cubes. It's a very regular surface. So what I'm going to do is, well, one thing that I didn't say is that for the normals, once you know, you redefine the Laplacian vector, which is now a different thing, you can apply again any polynomial of that operator into your data. So here I'm going to do Laplacian smoothing on the normals, and then in the first step, and you will see what happens, and then I will do this anisotropic filtering of the vertices using the normals to move in that direction. So first step is to filter the normals, and that's done. So you see that by just smoothing the normals, you actually get nice looking shapes, but the geometry has not changed. If we go close, you will see the squares. Well, it's too much, but you can see here that these are just a bunch of cubes where the faces have been painted with different color. But then we can do this anisotropic diffusion, which is again another filter in this newly defined Laplacian vector, which takes the same time, and the mesh gets smoothed and it integrates or tries to integrate the normals. Okay. And then, well, this I will just mention. I use this scheme to compress isosurfaces more efficiently. With our general polygon compression schemes, compressing the vertex coordinates is very expensive. I mean, compressing the connectivity is very efficient. We end up with 1 or 2 bits per triangle, but the vertex coordinates cost you much more, 5 times more. So in the average, if you use a polygon mesh coding scheme to encode these large meshes that you end up with when you run an isosurface algorithm, you still end up with very large data sets. But in here, I mean, based on what we saw in the previous example, just smoothing the boundary of the cubes may give you a very good approximation of the surface. So, and for that, the only thing you need to know is which voxels are inside and which voxels are outside, which means just 1 bit per voxel in the whole volume set. And in order to do that efficiently, well, I extended this for binary images. There is a very efficient image compression scheme. It's called JBig, and it's based on what is called context-based arithmetic coding. Essentially, you traverse the image in scan order, and every time you have to encode one of the bits, so it's a 0 or 1 that you have to encode in the bit stream, you use different probability model that is based on some of the previously received neighbors. So using a few of the bits that arrived before, you build a word, and that word indexes a table of different probability, a table of probabilities, and you keep updating that every time you receive a new vertex. In here, I use the same idea, except that because this is volumetric data, the layers are correlated, so you don't want to use it just layer by layer independently of each other. You use some of the bits in the previous layer to compute the context, and we end up saving about 50% of the data. So the end result is that these meshes, even though they have a lot of polygons, they cost you, I mean, with this encoding plus the smoothing that I showed in the previous scheme, you end up with these pictures in the decoder, and you pay something like half a bit per phase in terms of coding, which is extremely efficient. Okay, so I'm going to skip some things because there is no time. Another problem that I've been looking at is how to change the resolution of the mesh efficiently. People have been working in this problem of reducing the number of polygons for a long time, but with somehow heuristic approaches. Here I'm trying to define what it means to resample. And what it means to resample means that when you go from one resolution to another, you should be able to use the same process to go from the second to the first. And ideally, you will go back to the original data. So having this idea, I constructed a new algorithm that works for going from the primal mesh to the dual mesh. And there is some analysis of when that recovers the original data or not. But I'm going to skip this. The last topic I want to talk about is this other work that we have been doing this year that has to do with texture meshes. In addition to the geometry, people use texture mapping to put more details on the texture, as we did for the Pietà project. But this is a very common representation, mainly in games, where you have polygon meshes that are very small, and you put a lot of details on the texture. So in that case, how do you compress this data? You have to transmit it. You can compress the mesh with one of our methods, and then you take the image and you compress the image using JPEG. The end result is that the compressed image is 10 or 20 times bigger than the geometry now, or more. So there is something intrinsically wrong. The other thing is that typically people use very large and detailed textures and very small and coarse meshes. So one thing that people do is say, well, let's downsample the image, replace every 4 pixels by the average, and so on several times. And the results are terrible because you lose a lot of information. So our goal here was to, the bottom line, the most important thing here is that nobody looks at the images themselves. They only look at the texture map version of the image. So that if we have more freedom than just downsampling. We can warp the image or deform it so that we can assign more pixels to the areas of detail and less pixels to the area which are not interesting. For example, the face in the cheek is more or less the same color. You may want to reduce that region, while in the eye that there are some details, you may want to increase the area. So the question is how to do this efficiently and fast and simply, right? So that's what we did. I mean, I will explain this in a second. We defined a process that is a relaxation scheme that's very close to Laplacian smoothing, that essentially, after you define an importance map, it starts moving the pixels around, and you end up with a new image. You have to compute new texture coordinates, but ideally you end up with the same. You can downsample more efficiently. So here you have all of this. Well, there is another Java tool that we have to do this experiment. So in the left, you see the original texture and the rendering of the texture map model. On the right, you see the deformed image, and with new texture coordinates. In the bottom, you see here the rendering of this. Well, so because of resolution, we don't see the differences, but I'll show you something else. This is how it works. You somehow construct a new image that has some importance. So you say, I want a lot of pixels around the white areas and fewer pixels in the others. And now that we have to find a relaxation process that will actually move. So what we do here is we put a regular grid and we move it around to make it concentrate on the parts of interest, and then we invert the deformation, and that's what you see here. You see a big square around the eye in the right picture corresponds to a very small square on the left. Okay, so this is the idea of the warping. So you compute this importance function that in our case is a function of the geometry, the metric of the the shape, and the local frequency content of the image. So places with higher frequency content has to be expanded more, and places with low frequency content less. But you can also paint it. I mean, you can go to the picture and just paint the picture and say, I want a lot of detail here, I want less detail there. The bottom line is that you start with a regular grid and one of these importance map, and you want to end up with something like that on the right. We do that by minimizing that simple energy function. So the variables in the top are the location. So are the indices correspond to the nodes in the regular grid, and the nus are the location in the deformed grid on the left. And we just do gradient descent. I mean, you take the derivatives of that, and you end up with an expression that is very close to Laplacian smoothing, and it's very fast. And it corresponds, I mean, because of the fact that so the sum is over all the edges, ij, of the regular grid on the right. Because of the fact that there is always one parallel, one along the x-axis, one along the y-axis, this corresponds in the continuum to something like the expression in the bottom, which is closely to, anyway, we just do the discrete version on the top so far. And so this is the kind of things that you get. And once you do this, you have to invert, I mean, you have to compute a new image by inverting the mapping. And you also have to compute new texture coordinates so that the triangles correspond to the same thing. Yeah, John, I'm finishing in a second. And well, and here you see some results. I mean, it's a little difficult to see, but on the top, we just did the subsampling on the original texture. On the bottom, the subsampling after this optimization. And it's a little blurry there, but you can see that the details are preserved a lot. So, for example, these two pictures, the one on the left is rendered with a texture of that size. The one on the right is textured with a one texture that is 1/16 of the size, and so use fewer pixels. Okay, and then one last thing that I want to show is this work that we did at Caltech. When I was at Caltech last year on sabbatical, one of the things that I did was to organize this gadget lab, I mean, where the students would come, take a consumer device. I mean, the thing here is that all of these gadgets that we buy these days have powerful microprocessors inside, and so they are really computers. They are just programmed to do one thing. So what about reprogram them to do other things? So, and this is one of the projects that we did. I mean, for example, this camera that was introduced something like 4 years ago, look at all the things that it has. In addition to the CCD sensor, the image sensor has a lot of ports, has microphone, speaker, display, a powerful microprocessor, a hard disk, and it has an operating system that you can have actually access to. So it's a computer. So that's, and so here we have some pictures. The main thing is that all the algorithm is running in the camera. No? There is no other PC or anything here. So the turntable is connected to the camera through a serial port. I mean, we are using the simplest possible method to do 3D reconstruction that is based on the boundaries silhouettes. So the camera looks at the shadow of the object on the wall, and from those it recovers the shape. And then at the same time it looks at the left and gets the colors. And the camera works, it has, as a regular 2D digital camera, has two modes of operation. One is capturing, and this is what everything the camera is doing inside the camera. I mean, from these silhouettes, that defines a cone, and as the thing turns around, there are many cones that have to be intersected. This is done using a volumetric approach. The camera has to compute an isosurface, has to smooth the mesh, and at the end, compress the result and save it on disk. And then there is a viewer that is the same viewer that we had in Java that we ported to this. So you can open the file, load the mesh, and display it, and allows you to interact. Yeah, and this has been an evolution of this Java viewer. Anyway, just to point out something, these are telephones that they are selling in Japan. They have been selling for a year. They have more power than this camera, and they come with a camera inside, so you can do it in a telephone if you want. And can we do it camcorder? Yeah. I don't know. This is an open question. Nobody knows how to do this. I mean, have a device that goes around the objects and in real time recovers. I mean, Luis actually is working on some of it. Anyway, so that's all. Thanks.
Do you actually program this camera?
Well, there is this digital operating system that was developed by a company called Flashpoint. That I think that it's going down now. But you write it in C. They sell you a development environment that is very similar to Visual C++. You can even use GNU C++ to use C code. I mean, the only problem is to figure out, to have one running application so that then you can start modifying it. That's what the students did. Yeah. Yes.
In your basic Laplacian smoothing with the networks, it looked like there was some cusps forming.
Yeah, the connectivity. There are some problems with the valence of the vertices sometimes. The same thing happens in recursive subdivision. That when you have vertices that have three neighbors, there are cusps that do not disappear. So that with this second order thing, with using the normals, you don't see those artifacts. But yeah, in principle, you would like something that is independent of the connectivity, the discretization, but this is not. So some other people have been using more sophisticated methods, nonlinear and so on, where you can. I mean, so far I have been looking at these meshes as meshes, or forget about the continuum. But some other people say, well, this is actually discretization of the continuum version, and they do a more accurate approximation. I mean, these weights that are in the Laplacian smoothing here so far are function of the connectivity, which is not really what you want. So if you do that as a function of the geometry, you get a more accurate approximation. It works better, but it's more expensive.